It's not. So here's Lenz's law, right? So there's an induced current if the magnetic flux is changing. We know that. What is the direction? The direction of the induced current is such that the induced magnetic field opposes the change in flux. So B induced is related to I induced through the right-hand rule. The right-hand rule that you already learned for I creating a B, right? Except we're flipping now. We're doing B as the thumb and I as the fingers. So it's the same right-hand rule, but it's also a different right-hand rule, right? It makes sense it's reversed because the first one was for I creating B, and this one is for B creating I. So the creator is the thumb, and the result is the fingers. Yeah. Yeah, so this is where the opposing the change comes in. So how do we know the direction? We want to oppose the change that's going on. So let's do that. Let's look at this one. Okay? So we have a north pole of a magnet moving down. So B is pointing down and B is getting stronger. So the first thing we want to do is identify the change that's happening so that you know what the opposite of the change is, right? So let's identify the change. Identify the change. Okay? So that is B is increasing. B magnet. Let's call this B magnet is increasing. Okay? Do you see how it's increasing? Because the closer you get to the North Pole, the stronger the field. So we're bringing that North Pole closer and closer to the loop. Okay. I'm writing it on the wrong slide. I always do this. I did this last time. This is on the still slide, right? If we read the slide, it says it's being held still. Obviously, there's not going to be any change. Let me move this over there to the right, to the next slide. So it's not confused. There we go. There's our motion, right? I'm looking for this arrow here that tells us we're moving, right? Okay, so now same thing. Same idea. So identify the change. The change is that the B field is getting stronger and stronger near the loop, and that B field is pointing down. So if it's getting stronger and stronger, nature doesn't want that. It's going to oppose the change. And to oppose the strength pointing down, right, because the B field from the North Pole to the magnet is pointing down. To oppose that, nature is going to create a magnetic field out of thin air that points in the opposite direction, right? Like vector addition, right? If I have a vector pointing this way and it's getting big, how do I make it smaller? I add a vector pointing the other way, right? Because it's negative. So my B induced is going to point up. Yes, there's two. B induced, B mag is the magnetic, the real one, the one that we are creating, with the magnet, with our hands, right? Man's magnetic field. And then nature, or God, or whoever, creates this second magnetic field that opposes the change, and that magnetic field is responsible for the current, the induced current. So the subscripts are going to match. B induced will oppose the increase by setting a field, setting up a B induced field that points in the opposite direction. Sure. Quick question, direction. Huh? What'd you say?
So I understand the B one.
Okay. So now our thumb is in the B induced direction, which we know is going to point up. Okay? And our fingers are going to curl, our right hand, if we're looking down on it, our fingers are going to curl in the counterclockwise direction. Right? You're going to look down. Thumb is pointing up, B induced is pointing up, just like in the slides. And then look at the purple arrows. As viewed from above, that's counterclockwise motion. So the current induced is counterclockwise.
Counterclockwise as viewed from above.
Right, not to confuse you, but from below, that's a clockwise, okay? So we want to keep the same perspective, looking from above, unless otherwise noted. It's a common exam question to say, to give you this exact setup and say, what is the direction viewed from below? So be prepared for a perspective shift, okay? It's very common, to test the knowledge of the concept. And not memorization, right? If you notice, memorization, we kind of, the way we write tests in physics is to like make sure that you're not just memorizing things. That's like fundamentally what this class is here to teach you in addition to physics is problem solving skills and concepts and not memorization. And what sucks for you guys is a lot of your classes, your other classes that you take besides physics really rely on memorization. So it's a battle. That's why a lot of people struggle in this class. But I'm going to teach you not to rely on that, to rely on following the concepts through. So does that make sense? So let's do some more like that to make sure that, because then you can define a little bit of a cheat sheet, okay? So what I'll say is that if it's increasing, if the magnitude of B or if any part of the flux is increasing, then your B induced will point opposite to B, okay? That's always true. If your flux is decreasing, then B induced will point in the same direction as B. That you can always count on. So here's an example of an upward moving magnet. So the strong magnetic field near the pole is moving away. So B induced is going to reduce, right? B magnet is going to get smaller, right? It's going to reduce. So B mag is decreasing. So that means that B induced will point in the same direction as B to oppose the decrease, right? We're going to stop the bleeding and put more blood in the way, right? Right, we're going to stop the reduction by adding more B fields. Now you can see B induced is pointing down, right? The original direction of B magnet. It's like, no, let me add more vector to stop the decrease. So your thumb will point down. As viewed from above, that's clockwise. Whenever your thumb points down, you're looking at your hand from above, that's clockwise. Okay, so that's the general rule is a decreasing flux, you'll put your B field, your B induced in the same direction as the B field that's already there. And if your flux is increasing, you'll point your B induced opposite to the B field that's already there. So when you have it in that, like coupled like that, it's pretty easy. So let's do, this is kind of what I was, follow these 3 steps, right? These are kind of the steps that I've been outlining, right? Determine the magnetic field direction, find how the flux is changing. Is it increasing, decreasing, or staying the same? And it's going to oppose the change. So an increasing flux, the induced magnetic field points opposite. If it's decreasing flux, the induced magnetic field points same. It's very easy to grasp with those 3 concepts there. And then the right-hand rule, you can do that all day long. So let's do this one. All right, so now we don't have any magnetic field lines. We'll have to use our knowledge of how magnetic fields come out of bar magnets, okay? So North Pole is pointing up. That means our magnetic field lines coming from the North Pole are going to be going like this, right? Away from north towards south. So this is our B magnet. The North Pole is getting closer to the loop. So that means B is increasing.
And then our B induced is going to oppose the increase by setting up a field in the opposite direction.
So we're filling this point down and just making sure we're looking at the right perspective as viewed from above. If it doesn't say, you're going to do as viewed from above, and that's clockwise.
So we're always going the opposite.
Not always. I mean, so what's opposite is you're opposing the change, which could mean pointing in the same B field direction if it's decreasing, right? If you have a vector that's pointing up and that vector is shrinking in magnitude, the way you oppose that is by adding more in the same direction. So your B fields won't always be in the opposite. Don't think of it that way. Think of it as versus increasing or decreasing. So what do we say? We said clockwise, right?
So as the magnetic field is
No, the flux, if the magnetic field is increasing, then the flux is increasing as well. Okay? And then B induced is going to point in the opposite direction of the increase to oppose the increase. B induced, which is the B field responsible for creating I induced.
which is why
Yes, yeah. So the I that we're finding has a subscript. It's induced. It's not the magnet's, I, right? It's the induced magnetic field's I. The ghost I. You can assume that it means, it should ask for induced current. I mean, I guess, does it say current? No, it doesn't. There is a clockwise, yeah, it does call it induced. It will be called induced current. Yeah. Okay, what about this? Let's draw the field lines. Okay, when you're right here, the field lines are pointing horizontal to A, right? A vector is this way, B vector is this way, angle between them is 0. Is 90, which makes cosine 0. That's what I meant. Right? So the B field, there is, right, as you bring it closer and closer, is the B field changing in the loop? No, it's just, the flux is, is the flux changing? No, because you are going to have 0 flux the whole time you're bringing that magnet up. So there is no flux change. Okay. Okay, here we go. So, bar magnet, you can see the north pole is inside there. Okay, and so let's read carefully. A bar sits inside of the coil. For each of the following circumstances, what can we say about the current in the meter? So we're going to look at 1, 2, 3, 4 and identify if it's A, B, or C for 1, 2, and 3, and 4. So while the bar magnet is at rest in the coil, what's happening? There is no flux change, right? Because B is not changing, and the area of the coil is obviously not changing, and we're not changing the angle in between, right? So there is no current, so this will be C. So now, what happens if we pull the bar magnet out of the loop? So our B field is pointing to the left, right? This is the B field of the magnet. And as the bar magnet is pulled out of the thing, the strong magnetic field near the North Pole is going to be pulled farther away from the loop, decreasing B. So B is pointing to the left, B is decreasing. So what direction
is the induced magnetic field gonna point to oppose decrease? In the same, right? Yes, in the same. So I'm gonna draw my B induced in red. My B induced is gonna point in the same direction. And so then I'll put my thumb in that direction, and then I'll curl my fingers. So from the front to the back. Okay, going up from the front to the back, going up. So let's trace out what that means. So if my current is going this way, that means it's going this way. Okay, that means it came from this way. That means it's going this way. So my I induced is gonna be going from right to left. Does that make sense? I kind of had to trace it back, right? You start with your curly part that you know, and then you trace it down the line to see what direction it's flowing through the meter. So that's going to be an I pointing in the same direction from left to right, which is B. Let's put our answers over here. Okay. When the magnet is completely out of the coil and at rest, no flux change, right? And then now when we put the magnet back into the coil, I think you can, put the logic together. Obviously the current's gonna be pointing in the other direction, but let's just verify it, okay? So when you are pointing the magnet back into the coil, well, B-mag has not changed its direction, right? Because we didn't flip that magnet around. But now B-mag is increasing. And so that means B induced, we want to oppose, nature wants to oppose that with a magnetic field pointing in the opposite direction. Okay, so that means our current's going to come from the back of the loop towards the front of the loop going down. So I'll use a green for that. So it's coming from the back of the loop to the front, back of the loop to the front, back of the loop to the front. So I'm tracing this back, tracing it back. So it's gonna go from left to right. Oh, did I say right? Okay, hold on, sorry. Right? I can't, my poor directions, no one caught me here. This is A, right? Right to, orange current is right to left. Okay. Purple current, or green current is left to right. Is that right? Okay, there we go. Right to left. Left to right. Oh my God, stop. It's like once the switch in my mind flips, it's like anything that's 50-50 is like constantly oscillating. Yes.
Okay, now I'm confused.
Yeah.
So when you're tracing it in the loop, like, how can you see left and right?
Okay, for the green one?
No,
Oh, for the orange one?
Like, I can get there.
Okay.
But when you're pointing in a direction, like.
Okay, let's look at the orange current. So the orange current came from the induced pointing to the left. Which is the red, the orange current, right? The induced is pointing to the left. And then I'm taking my fingers and they're in front of the cylinder, whatever it is, and then going to the back on their way up. So I'm pretty sure I traced it, yeah. So I traced them all. Let's follow, right? They're going like this. Let's follow it all the way. Boom. See that? I kind of went backwards, and that maybe was confusing. I traced it backwards, but just follow the whole thing. Yes, yeah. For that, so orange is from right to left, green is from left to right. So it gets progressively more difficult because they stop giving you the B field direction, right? And you're gonna have to use your knowledge of the previous chapter to determine the B field direction. So, and that's where we use the North Pole, the magnetic field, right? We know that it points out of the North Pole. All right, what about this? So we got a magnetic field going through a loop of wire. Okay, magnetic field, the X's mean pointing into the page. So B is pointing into the page, B of whatever the magnet, whatever is creating that, right? Into page. Okay, and so if the magnitude of the magnetic field is increasing, decreasing, or constant, what are the directions of the current? So if B mag is increasing, then B induced, let me use a different color, B induced will point in which direction?
To oppose the increase. Right. Opposing vectors into the page by applying a vector out of the page, right? Opposing the increase. So our thumb will be out of the page, opposite of B, magnet, and we're going to have a counterclockwise. Okay.
And then I counterclockwise. If the magnetic field is decreasing, the opposite. B induced will be into the page, the same as the original magnetic field, because that B field that's pointing into the page is getting smaller, so we need to add more in the same direction to oppose the decrease. Thumb into the page, look at your fingers from the outside here, and they're curling and clockwise. But you might have already guessed that just by using logic. And then obviously if the B field is constant, then you have no current because the flux is not changing at all. Okay. Here, okay, yeah, here's what we were talking about where it's moving out. It's moving completely out, right? No ambiguity here. So we're taking this loop. Okay, B is constant, flowing into the page, and we're taking the loop and we're yanking it out of the magnetic field. So the flux is decreasing, right? Because the area is decreasing. Area exposed to B is decreasing. Flux is decreasing. And so B induced will point in the same direction as B. B magnet, right? Whatever this B is, mag. And so then in the page, we're gonna have a clockwise current. So there's like a million configurations of this, what we're doing right now. And I put a bunch in the practice exam. So, I mean, there's like, the practice exam is very long. It's not really a practice exam, it's practice for the exam. But I put a bunch in there so you can keep practicing. Okay, here's a good, oh, I like this one. Okay, so like multiples, concepts on concepts. Okay, so we're bringing a wire loop towards a wire. Okay, so what's going on here? Is there going to be a flux? Okay, like no, the magnets are gone, right? Now the source of the magnetic field is the current carrying wire. So the current carrying wire is going to create a magnetic field, thumb in the direction of I, right? We're doing two different right hand rolls at the same time. Current in the direction of your thumb, the magnetic field due to that current is pointing into the page above the current. So we're going to put some X's for the B field created by that current. Now what do we know about its magnitude? Right? The B field right here is mu naught I over 2 pi r. And as r gets bigger, B gets smaller, right? So we have weak B up here, strong B down here. I'll call this B wire, just to keep them separate. So what is happening to our B? Our B is increasing. Our B wire is increasing as we bring the loop towards the wire, right? And
And so Lenz's law tells us that nature will create an induced magnetic field to oppose that increase by setting up a field in the opposite direction out of the cage. And that gives us a counterclockwise loop. Okay. So we've done a lot of directional. Let me see what this is. Well, I think this will be a do at home so we can move on and go from direction to magnitude, right? So we spent a lot of time finding the direction of the current. Well, what's the magnitude of that current? Faraday's law tells us the magnitude. So we'll do these at home. There's 1,000 of them because there needs to be. Because there's so many configurations. What was what? Oh, Faraday's law gives you the magnitude of the current. Lenz's law tells us the direction. So, yes, so we're going to get into Faraday's law next. They put Faraday's law, okay, there we go. Yeah, so Faraday's law, you can get the magnitude of that current. Whereas Lenz's law gives you the direction of the current. Calculating the magnitude is fun and easy. How do we get a current? We get a current by creating a potential difference and pushing that current through a resistor, right? So this is V equals IR right here, where V is that epsilon, which represents the battery's rating, right? Remember, that's like how if it's 1.5 volt battery, then epsilon or the EMF is 1.5 volts. So this is simply a voltage, but the reason why we use script E is we're denoting it as a source of motion for the current, right? This voltage is creating motion. It's getting those current, that the molecules or the ions to move, the electrons, whatever they are, okay? So Faraday's law, it's real easy. It's simply the change in flux with respect to time. And so how do we calculate the flux? It's the BA cosine theta, right? But it's a change, so it's, maybe we should write this as, BA cosine theta final minus BA cosine theta initial, right? These values are going to change. And that change, one of those changes is going to create our EMF, which is going to create the induced current. And then say over the time, right? The time it took to make that change. Right, so we can change the flux by changing B, you can change the flux by changing A, and you can change the flux by changing theta, okay? We're not gonna have a situation where we do more than one at the same time. It'll just be one at a time, okay? We're not equipped to do more than one at a time. Because then you gotta do some crazy calculus math. So if there is more than one loop, right? Because we saw a situation that was just one loop floating around, and we saw a situation where you had a solenoid that had multiple loops. If there's multiple loops, you just multiply by the number of loops. So this would be in a case of like a multi-loop thing like this, okay? Where you have your magnet and you're, pulling it in and out, right? Where we have multiple loops being exposed to that flux change. So it's just gonna get multiplied through. Okay, so there are two fundamentally different ways to change the magnetic flux through a loop. You can change the loop size, you can change the magnetic field. I don't know why they don't have the current listed there. I guess technically the rotation part. This is incorporating both A change and theta change. Okay, I like to say it's all three, but separate, but, right? Because they're saying the loop can expand or rotate. So that's telling you it's both theta or A changing. Okay, so we're gonna examine all that. So here we go. So here's our problem solving strategies, which we'll talk about when we do examples. So let's look at this. So let me get some room here. Okay, so we're gonna practice calculating changing flux. So we have a patient getting an MRI scan and they did not remove their bracelet. And we're gonna see what happens to them. Okay, so, and this is not an issue with the magnetic thing, right? Because I'm sure you've heard the horror stories of people leaving a magnetic object on their body while getting an MRI. And the MRI machine produces multiple Tesla, this is 1 Tesla here, which will be enough to take that magnetic object and pull it towards the magnet in the MRI. But there's another situation, maybe that you didn't think of, is that what if you're wearing a bracelet and then you get a current induced around your arm, right? Well, that bracelet's gonna heat up, right? Whenever you have current flowing through wires, the wires get warm. That's why we cover them with insulating material, right? So you're gonna have a hot bracelet on your hand, right? So we're in the MRI machine, which, I don't know if you've been in one. It's a big old tube, okay? It's a big tube, and the magnetic field is in the axial direction, okay? So inside this tube, we have our copper bracelet of radius 6 meters. Oh, diameter 6 meters. So radius 3 centimeters. Okay, that's our bracelet inside of the MRI machine. And then let me use little r for that, because big R is going to be the resistance of the bracelet. And then the solenoid is directed along the person's body from head to foot, and her bracelet is perpendicular to B. That's pretty much what I set up here, right? They're laying down. You know, the bracelet I drew in a floating around, but there's a human here, like there's a human arm here, right? And their body is laying down. You know, I'm really bad at drawing people, but, right, you got the idea, right? They're laying down in that tube, and B is going through that bracelet. So, oops, I keep deleting that. Let me delete the black things that I wrote. My eraser pen is too big. There we go. So B is going perpendicular through this hoop here. We don't know which direction. It doesn't matter. So as the scan is taken, the B field decreases from 1 Tesla to 0.4 Tesla in 1.2 seconds. The question is, what is the magnitude and direction of the current induced in the bracelet? So let's pick B pointing out. Okay, we can just pick one. It works both ways because we're told that B is decreasing, right? So let's pick B as pointing out, and then our area vector is also pointing out. And so this B field is getting smaller, right? So we have our induced EMF is created by the change in flux with respect to time. Okay, the time change we saw was 1.2 seconds. The change in flux is going to be flux final minus flux initial. So let's calculate flux final. It's B a cosine of 0. B is the final, right, is 0.4 Tesla. The area is pi times 0.03 squared. Okay, and then cosine of 0 is 1. So let's get a value for that. So it's a 1.13 times 10 to the minus 1, 2, 3
Webers, right? Flux is a Tesla times a meter squared, which is a Weber. So now let's find our initial flux. Same thing, starting at 1 Tesla. The angle is not changing. So then we can calculate the EMF, which is going to be 1.13 minus 2.83 times 10 to the minus 3 Webers divided by the time. So it's going to be negative, but the negative doesn't really, it's like, you know what I mean? The negative, we're always going to be doing magnitude, I forgot. So don't worry about that. But just make sure that the negative is there when you're subtracting them, but the result, we just care about the, you know, the final result, the magnitude. So that is 1.13 minus 2.83. So it's 1.7 times 10 to the minus 3 Webers. Okay, finally, this is going to be a voltage. A Weber divided by a second is a voltage. If you didn't know that, now you know. The units get real chunky. Okay, so this is our voltage. 1.42 times 10 to the minus 3 volts. Okay, not a huge voltage. So that voltage is being, and you're probably like, well, where's the voltage, right? Here's a blow up of our copper bracelet. This voltage is acting everywhere, okay? Causing a current to flow, right? This voltage is acting in a kind of in a circular direction, making the current flow in that circular direction, okay? Now, which direction? We need to, sorry, my phone is like ringing. I hear vibration, stop. So we need to figure that out, okay? Oh no, we want to find the current value. Let's find the current value, because that's just the voltage, right? V equals IR. So let's see how much current is flowing through that person's bracelet. And then the resistance of the bracelet was 0.01 ohms, okay? Which is going to make that a big current, right? Because they're dividing by a fraction. $142 milliamps. Okay, it's a pretty significant current. Okay. I do think it can go to human skin. I think that's enough current that would, you know, be transferred if that bracelet is touching your skin. That person would feel current flow. Okay, it would probably start to flow through them, but it would also heat up that bracelet and make it get warm while they're getting a scan, which is not great, right? So because copper isn't magnetic, it's not going to fly off into the MRI, but it is going to induce a current and potentially heat up and burn the patient or get them zapped, okay? So what is the direction? So let's say that B is pointing to the right. That was let's just assume it's pointing to the right. B is decreasing, okay? So that means B induced. B is decreasing, which means B induced is going to point in the same direction as B to oppose the decrease. And if B induced is pointing in the direction of B, then the current is going to flow out of the page to us, right? So if we're looking at it from outside of the MRI, the current is going to flow counterclockwise. Okay, so this is where the perspective is changing, right? Our eye is over here. our beautiful eye, right, looking at this, and what we're gonna see is counterclockwise current. So this was just my showing, right, so it's technically going this way. This is hard to draw 3D. Okay, let me see if I can draw it 3D. I don't know, right, I'm trying to make it like thicker up here. Okay, counterclockwise. Okay, any questions about that? The calculation part, not terrible, right? Yes.
And according to the slides, it says it's like clockwise because the direction of B is actually supposed to be the other.
Oh, okay.
That's why
Either
it's
way
a
works.
problem.
So we can do that. If we want to match the what they chose, then let's do that. B is pointing this way. B induced pointing this way. And then as viewed from, still from that same perspective, you can see that it would change it to clockwise, right? Because B induced would point this way, and then if you're looking at your hand like that, it's clockwise. So, we didn't know what direction B was pointing. I know it points axially, we just picked one, you know. And the exam, it would be very clear. Okay, which one you leave it up to. So, yes. Oh, okay, yeah, it would not be like, here's a mysterious machine and what direction is the B field? You know, like, here's a machine, you never really thought about that. Does it say, it points, oh, from head to toe, maybe that's, the clue is in this head to toe part. Because from head to toe, and we're assuming their head goes in first. Oh, well then, that makes mine better. That makes mine make more sense, right? But don't worry about that. That's like not a relevant part of the problem, right? That's not relevant. You pick the B, and then you know what direction, it is. It's either axially out or axially the other way. So, yeah, it's directed along the person's body from head to foot. But, do you go in feet first? I thought you go in head first. I don't know, I've never had an MRI.
She's not on those, so it's like you go in and then you sit. So it's like,
Yeah.
It still wouldn't.
Yeah, it's not clear, right? The question's not clear. Okay. But it's a non-issue. It would be clear on the exam for sure. And they're drawing it from a cross-sectional view. I kind of drew it from a side view. Okay. So, lots more examples, okay? So, eddy currents, don't worry too much about, okay? But I'll tell you, I'm not gonna ask any questions, but let me explain what an eddy current is. So, well, as you saw, there was a current formed in that bracelet, right? That's an eddy current. So that is a current flowing through a conductor, and the source of that current flowing through a conductor was not a battery, it was not a power supply, it was a changing magnetic field, okay? So that's all an eddy current is. It's an induced current that is flowing in a conductor. And so these eddy currents, they're used actually in metal detection. This is how a old school metal detector works, is what you're doing is you're walking through a magnet, and if the flux changes as you walk through, that means that you have metal on you, okay? And the detector goes off. And and how does it know you have metal on you? Because even though you're not wearing a bracelet, that metal is gonna have a current induced, and that current induced is gonna create its own magnetic field, right? And that magnetic field is gonna interact with the metal detector device and say, hey, something's here. There's something present. And it's metal. Okay, so just kind of a fun application. Don't worry too much about eddy currents. All right. I'm not going to test you on it. So this is a good example. So do it, huh? So now we can, we don't have much time, but we can talk about it next class. So we're going to talk about electromagnetic waves, okay? And let me give you the punchline here. So you know that an EMF,
let's just back up a little bit. You know that an EMF is a voltage, right? And a voltage is related to an electric field, right? A voltage is created when there is an electric field that is pushing, right? You have separation of charges, that creates a voltage, and your electric field points from positive to negative, right? So think of that EMF as an electric field. And so basically what we've done is we've gone full circle. We've said that currents, which are created by electric fields, produce magnetic fields. So electric fields produce magnetic fields. We just saw that a time-varying magnetic field produces a voltage, which is an electric field, right? So this is how electromagnetic fields are born. They're born from the cyclical process. E field creates a B field. B field creates an E field. E field creates a B field, and it goes on forever and ever. This is why electromagnetic waves from outer space, from, you know, millions of light years away, eventually make it to us. Like nothing, how did they have all that energy to get over here? Because they're constantly creating their own energy by creating the B field, which causes the E field to move, which causes the B field to move, and so on and so forth. So we're kind of taking now like the culmination of all this, right? E fields creating B fields, B fields creating E fields, electromagnetic waves are born. So this is going through, you know, we'll talk about this more about exactly how all that fits into the tools that we've been learning about, which are solenoids and current rings and magnetic fields. Okay, so we'll talk about that. But I just wanted to give you the punchline, right? Why we're looking at this. It's really, you know, straightforward after this. Velocity of an electromagnetic wave. Okay, we're going to talk about that. We're going to talk about the E field and the B fields existing at the same time. And you're going to see that they're always perpendicular to each other at all times. Okay? Light is an electromagnetic wave. And so we'll talk more about this next time. Okay? And let me know if you have any questions.